Is it visible na po?
Yes, yes.
Yes, yes.
Okay. So good afternoon, everyone. I'm Stephanie Vergara, and I would like to thank you all for being here. And I'm hoping that you'll be able to learn something from me and my study. So, through the concept of a segmented telescope system, the effects of varying the distances in between two identical mirrors were simulated. Furthermore, a circular and a parabolic configuration of the two mirrors were adopted and investigated using the point spread function. Based on the results, the addition of mirrors improved the quality of the image by increasing its intensity. However, the effect suffers when the mirrors are beyond a critical separation distance. So here is the outline of my presentation. Let us start with the question, what is a telescope? So a telescope is an optical instrument used for viewing distant objects. It is the most common instrument used to study and marvel at the universe. But how does it work? So a telescope works like a bucket in the rain, gathering light from the source or the object to be imaged. This bucket has a funnel at its bottom, which focuses most of the light gathered into our eyes. Okay, the bucket is called the objective, the funnel is called the eyepiece, and the bucket's opening is known to be the aperture. So these are the parts, the main parts of a telescope. Uh, as the bucket increases and its opening also increases, the amount of water collected increases. Similarly, as the telescope's objective and aperture increases, the amount of light it can gather also increases. Right. So why do we need to gather more light? Let's look at this example in this slide. So figure 2 shows the Orion constellation, which can be seen by our naked eye during a clear night sky with minimal light pollution, of course. What most of us don't know is that through the aid of some telescopes, the light shining from the Orion Nebula can be seen. So, a telescope can be used to make the things unseen to the unaided eye observable. Another example of a telescope's use is illustrated here. So, figure 4 shows an image of a bright object in the night sky. But when you look at it with a telescope, you will be able to recognize this object as Saturn. So in other words, a telescope can make faint, blurry objects recognizable. Now my question is, how did the idea of a telescope come to develop? For that, we have to go back to our roots. So optics is the branch of physics that studies the properties and behavior of light, including its interactions with matter and the construction of instruments that use or detect it. So optics began with the development of lenses by the ancient Mesopotamian people and ancient Egyptians, excuse me, followed by the theories on light and vision developed by the ancient Greek philosophers, and the successful experiments done by ancient Arab scientists. Thousands of years later, these scientific discoveries were used by a Dutch spectacle maker known as Hans de Perche, who received the first patent for the design of a spyglass used for magnification in 1608. So there. A year after, in 1609, Galileo Galilei, seen in this figure here, he's the one standing. Uh, he is demonstrating his instrument to the Duke of Venice. So Galileo Galilei made his own version of the spyglass. He called it a telescope, and he used it for his astronomical discoveries. Galileo's design has then been very popular and celebrated since it was first of its kind and caliber. Excuse me. However, his design suffered from manufacturing difficulties and produced blurry images of stars surrounded by colorful halos. Another problem of Galileo's design was that the field of view is very small, as can be seen from figures 8 and 9. Since it is dependent on the size of the lens, on the size of the lenses used. Uh, this uh, uh, this problem opted early astronomers to construct bigger and longer telescopes for better magnification, but was accompanied with more aberrations. So it wasn't until 1668 when Sir Isaac Newton, who was at that time working on his theory that white light is composed of a spectrum of colors, argued that the lenses used in early telescope designs behaved like prisms in that it is breaking white light into different colors around bright astronomical objects. This aberration is known now to be chromatic aberration. Ayan. So to correct this, Isaac Newton used mirrors and thus he built the first reflecting telescope. He also simplified construction by devising ways to shape and grind the mirror here uh, to polish the optical surface into a spherical shape so that when light hits the mirror, it focuses at this point. Excuse me. Even though this choice would introduce spherical aberration, it would still correct chromatic aberration, which was groundbreaking at that time. Okay, so in general, no matter what configuration, a larger aperture telescope, excuse me, a larger aperture telescope will be able to gather more light to produce better images. In manufacturing large aperture telescopes, however, there are difficulties for refractors since its primary lens can only be supported on its side, as is evident in the image shown here. So thus, increasing the diameter of this lens can result to the lens sagging under its own weight. Meanwhile, reflectors or telescopes that use mirrors can support significantly larger scales. However, it is still subject to structural issues when faced with even larger apertures. Aside from that, both types of telescopes are subject to extremely expensive production, fabrication, and maintenance just for the primary mirrors alone. So to solve this dilemma, the segmented telescope system was devised. So a segmented telescope works by multiplying the amount of light gathered through additional segments. So you can think of it as like increasing the number of buckets to collect the rainwater instead of using a large one. So segmented mirror telescopes paved the way for extremely large telescopes and is the basis for the construction of the next generation telescopes, such as the recently launched James Webb Telescope, which has just successfully unfolded its segmented mirror setup in space. Yeah. So that being said, the results of this study can help us in developing a segmented mirror system of our own. So the study's objective is to determine the relationship of varying the alignment, distance, and quantity of mirrors of a segmented telescope to the quality of the image produced. Here are the main references that I used. So the first one is a study conducted by Alagao et al. Regarding a segmented telescope using identical mirrors. The second one by Richards and Wolf is the basis for the algorithm I used to simulate the image formed at the focus. The third one explains the point spread function or the PSF. So what is the point spread function? A point spread function is how a single point of light will appear on the screen after passing through an aperture, as shown in this figure. So the point spread function is a J1 Bessel function, which looks like concentric circles, representing the airy disk of the image. So the airy disk, as seen here, is used to describe the best focus spot of light that an optical system with a circular aperture can make, limited by the diffraction of light. So below the airy disk is a cross-section of the intensity profile where we introduce another important concept, which is the full width at half maximum, or FWHM. So it speaks for itself. It's the full width of this peak at half maximum. So there. For an ideal telescope, the ideal, excuse me, the ideal airy disk is clear concentric circles and a lower FWHM, which both describes a sharper image at the focal point, which results to a better image. So for the methodology, I simulated 4 different setups. The optical instruments used have a focal length of 300 millimeters, and the wavelength generated was at 400 nanometers. So for the first setup, a 1-mirror telescope was simulated with an effective diameter of 152 millimeters, which is twice the diameter of the segments in the following configurations. Excuse me. For the second setup, 2 mirrors placed side by side was simulated and the distance d between them was increased. For the third setup, it involves a derivation of the parabolic equation. So the assumption here is that the mirrors lying in a excuse me, in a parabolic configuration would focus at the same point. The equation used is derived from the general equation of a parabola given in equation 1. With the vertex set at the origin and the focus derived from the focal length of the mirror used. The separation, D, is measured along the horizontal axis as shown in this figure. So from equations 1, 3, and 5, an expression for the constant A can be calculated and was solved to be 1 over 1,200. Substituting this value to the original equation, we now have an expression for the parabolic equation used to be used for the translation of the mirror in the xy plane. Now from equation 7, derived earlier, the tilt angle of the second mirror is solved by getting the derivative of the expression here, which corresponds to the slope of the tangent line along the parabola. Finally, to get the tilt angle of the second mirror, we solve for the derivatives inverse tangent. For the final setup for the circular configuration, the same methods were used, starting with the general equation for a circle, as shown here in equation 10. So again, the vertex is set in the origin and the focus is derived from the focal length of the mirror used. So by substituting the known values, we arrive at an expression for the circular equation to be used for the translation of the mirror in the xy plane, where A here is just equal to the focal length of the mirror, as can be seen in equation 16. Similarly, the slope was derived from the derivative of the equation and the tilt angle was calculated from the inverse tangent of the derivative. Lastly, it is also noted that for the third and fourth setup, which is the parabolic and the circular configurations, the second mirror was placed at distances with 38 millimeters up to 100 millimeters. 38 millimeters up to 150 millimeters. Okay, so for the results, we'll start with the 1 mirror setup. So, okay, Here are the results for the first setup with one mirror. So the actual view of the point spread function, as can be seen on the left, represents the intensity at the image produced, while the transverse view, seen on the right, represents the translation of the projected image. Excuse me. These figures are normalized to the intensity of the configuration when the distance of the two mirrors is equal to 0. So results of the one mirror setup show that the maximum intensity shown here of the PSF is at 0.568, normalized to the configuration with a distance of 0. So here is the maximum intensity for the axial and the transverse, which is just the same point. Meanwhile, the full width at half max of the setup was measured to be 3.026 for the axial view and 2.197 millimeters for the transverse view. The images shown are the air disk of the image with its corresponding cross-section intensity profile located underneath it, which is what was discussed earlier regarding the point spread function. Okay, so for the two mirror setup, arranged side by side, the separation distances used were 60 millimeters through 160 millimeters in increments of 5. Now, for the point spread function of the mirrors placed side by side, for the actual view for this part, it is apparent that as the distance increases, the foci of the segment, which is this circle here, starts to diverge and the intensity starts to decrease. So for reference, this is the point at 60 millimeters, 65, 70, 75, and so on. So as we can see, the focus of the mirrors of the segmented mirror system start to diverge at this point and then continuously diverges as the distance increases. Okay. Now for the point spread function of the mirrors placed side by side for the transverse view, again, it is apparent that as the distance between the mirrors increase, the foci of the segment also start to diverge, and the intensity of the area disk, which is the circle here, decreases. So furthermore, at a distance of 95 millimeters, so here, this is the distance of 95 millimeters, the two peaks of the two segmented, of the two mirrors appear to have diverged completely. So we can clearly see the two red dots, which represents the peaks of the intensities. Meanwhile, at 120 millimeters, the area disk of the two mirrors are now separated. So here is the plot at 120 millimeters. It is now separated and they continue to move further apart, excuse me, as the distance in between the mirrors increase. So for the circular and the parabolic configurations, they were simulated with distances from 38 millimeters through 150 millimeters. So shown in this figure, however, are the plots at distances 38 millimeters found here in the upper left corner through 150 millimeters found here at the bottom corner in increments of 10, because I can't show them all here. So there are a total of 75 PSF plots produced for this configuration. Thus, these distances used were chosen since they exhibit significant parts of the results. So moving on to the third setup, the parabolic configuration, figure 21 shows the result of the said system for the action view with the same distances mentioned earlier. So for the point spread function of the mirrors, it is apparent that as the distance between the mirrors increase, again, the intensity of the light at the focus decreases and the foci of the segments start to diverge. Furthermore, at a distance of around 108 millimeters here in this figure here, the peaks of the intensities start to appear again after disappearing around these distances. This could signal the separation. This could be due to the fact that the peaks of the two segments are now starting to diverge. Excuse me. Also, at the last three PSF profiles, it is apparent that once the area disk of the two mirrors have separated, the second mirror here appears fainter and fainter as the distance increases. Okay, so for the results of the parabolic configuration system for the transverse view, with the same distances mentioned earlier, the point spread function shows that it is apparent still that as the distance increases, the intensity of the light at the focus decreases, and the foci of the segments start to diverge. Similarly, at a distance of 108 millimeters, the peaks of the intensity start to appear again, signaling the separation between the foci of the two mirrors. For the last configuration, we have the circular configuration. For this slide, we are going to discuss its actual view. Okay, so from the figure, it is still very apparent that as the distance between the mirrors increase, the foci of the segment also start to diverge, and the focus starts to decrease. And the intensity of the light at the focus starts to decrease. Sorry. Similarly, at the same distance, 108 millimeters, the peak of the intensities of one mirror starts to appear again, signaling the separation between the foci of the two mirrors. The focus of the second mirror then starts to appear fainter and fainter as the distance increases. And at 140 millimeter distance, the focus of the second mirror completely disappeared. Finally, for the point spread function of the mirrors lying in the circular configuration, for the transverse view, it is still very apparent that as the distance between the mirrors increase, the foci of the segments diverge and the intensities decrease. Similarly, at a distance of 108 millimeters, the peak of the intensity of one mirror starts to appear again, signaling the separation between the foci of the two mirrors. So the focus of the second mirror then starts to appear fainter and fainter as the distances increases. For the intensity versus the distance plots, we can see that relative to the nearest distance, which is 38 millimeters, the intensity of each configuration all decrease as the distance increases. However, at the 95 millimeter point, we can see a slight but steady increase, which corresponds to the focus of the second mirror, which corresponds to the point where the two peaks has separated. The intensity then decreases again as a result of the separation of the focus of the second mirror from the first. So from this plot, from these plots, there is a critical effective separation distance, which deems the second mirror to have no more contribution to the focus of the image at the first mirror. Lastly, the plots comparing the full width at half max of each distance for each configuration is shown here. So both the circular and parabolic configurations exhibit the same trend. For the axial, which is the blue line, and for the transverse, which is the orange line. So let's first talk about the axial. So for the axial, the nearest distance simulated produced the smallest full width at half max. This is to be expected since as the foci of the segmented system start to diverge, the airy disk of the point spread function starts to stretch, which results in a larger full width at half max and a less focused and less intense image. And then as the two foci separate, the full width at half max decreases, as shown here in this trend, since it is now only showing the intensity of a single mirror. Meanwhile, for the transverse intensities, which is represented by the orange line, it is not the smallest distance that results to the lowest full width at half max. So according to the data gathered, the distances with the lowest full width at half max for the circular configuration is around 48 millimeters up to 54 millimeters. And for the parabolic configuration, the distances range from 55 millimeters to 60 millimeters. After these points, the full width at half max of each configuration starts to increase as a result of the foci gradually separating from each other. Thus, the airy disk pattern, thus stretching the airy disk pattern, resulting in a larger full width at half max. After reaching again its peak, the full width at half max now starts to decrease again, which is a result of the complete separation of the airy disk of the two mirrors. So for the summary and conclusion, the results of the study showed that adding another mirror increases the axial and the transverse intensities up to a certain critical separation distance. Moreover, a higher intensity means the telescope is more capable of gathering light. Thus, it is much more capable of producing better quality images from further or fainter light sources. In other words, the construction of primary mirrors of a segmented telescope would have an effective separation distance. More than this value will result to a faint and blurry image at the focal plane of the optical system. Lastly, the results showed that for the axial view, the shortest the shortest distance gives the smallest full width at half max value. Again, a smaller full width at half max means the light gathered from the point source is more focused at the optical system's focal plane, which is what we want. So meanwhile, for the transverse view, it is not the smallest distance that results to the lowest full width at half max, but the distances from 48 millimeters to 54 millimeters for the circular configuration and 55 millimeters to 60 millimeters for the parabolic configuration. And lastly, for the recommendations, it is recommended to study the effects of adding more mirrors to the segmented telescope system for the two configurations, the circular and the parabolic. It is also recommended to investigate the effects of using non-identical mirrors in the segmented telescope system. So with that, here are my references. Here are my image sources, and thank you very much for listening. I am now ready for questions.
Okay, thank you, Stephanie. The floor is now open for your question, Stephanie. Maybe let's start with the panel. Okay, I'll start first. Maybe let's go to the basics first. Can you explain again how does segmented mirror reduce the size of a telescope?
Sorry, sir.
Can you explain again how segmented mirrors reduce the size of a telescope?
Oh, using segmented mirrors. Wait, sorry. Okay. So by using additional mirrors, the amount of light gathered is multiplied. So in a sense, having a segmented telescope system would result to a to a light gathering power equivalent to a much larger aperture telescope. Since by adding the segments, the the amount of light gathered is increased significantly. Does that answer the question po?
Okay. So can you say that in using segmented mirrors, it's more cost effective than the traditional one mirror only?
Yes po.
Producing.
Yes po. Excuse me. But to a certain extent. So, for wait, sorry. Okay. So for certain uh, sizes of the aperture, I'm sorry for the pauses. For certain sizes of the aperture, it is more cost effective to use a segmented telescope since it will be harder to construct a very, very big primary mirror. So like for example, if you want if you want to image a star very far away, okay. Sorry, my thoughts are uh, a lot. Okay, so for example, for some observatories, they are okay with using monolithic telescopes, which is telescopes with only one mirror, since it's not as big as the extremely large telescopes, which is the trend now. So for the extremely large telescopes, it is not cost effective anymore to have monolithic primary mirrors or primary mirrors, since the amount of material that will be used to make a very, very big single mirror is more expensive compared to making, let's say, 7 or 18 segments of a smaller mirror.
Okay. Do you have approximations? Do you use approximations in your? So you use derivations, right? But you did not show it in your slides.
Sorry, sir.
Derivations, equations.
Oh, the derivation equations po.
Yeah. In your thesis, you have some derivations.
For is this the ano po for the diffraction theory?
Yeah, yeah.
Um,
What approximations did you use there, or is there any approximation?
For the first of all, I didn't include it in the slides po kasi it is from my main reference, which is the electromagnetic diffraction theory by Richardson Wolf. So the approximations used there were all based from the paper itself.
Okay, so do you know the approximations used?
I can't tell them now, sir. I'm sorry, I don't remember much of it, but I will take note of that
Okay.
when
So,
writing the
okay. The
manuscript.
usual approximation, di ba, is partial approximation. Yeah.
Yes po, yes po.
Okay. So maybe you can include it in your final manuscript. Okay. Next question. What does the PSF tells us again physically? So if you have, can you show your images results?
Our results po.
Yeah, then for example, so if you have um, those red dots, what does that mean physically? A sharper image?
Yeah, yeah, sorry. Yes po, sir. So the point spread function again is okay. So for the simulations, what I did was I assumed a point source, which is usually a star in real life. In real life. Uh, in real life. Sorry. So with the assumption that the star is a point source very far away, the uh, the the image that would be formed from the reflection at the optical system would should still be a point, since the source is also a point. So that's what the point spread function is representing in real life. So for these figures, um, uh, this circle represents the focus at the focal plane. So the red dot represents the focus, meaning na with the with the intensity being at 1. Okay. So here is the maximum intensity, which can be found at the focus of the setup.
Can you show yung circular and parabolic na result? Parabolic na lang. There. Yeah. Okay. So ideally, what do you want to achieve? So which image here? Yung gusto mo ma-achieve?
Yes.
Ideally po, the image that is supposed to be generated for the segmented system is the image here at the upper left po.
Okay.
It is the point where the two foci of the of the segments align at the same point. So nag-add up po yung intensities nila, resulting in more light gathering power.
Okay. So as you go from left to right dito sa figure mo, you increase the distance, right?
Yes po. Opo.
Okay. At tapos yung upper left corner is when the focus coincides.
Yes po.
Okay. So maybe yun lang muna for me. Sid.
Okay. Ako may question. I have a question about this. Punta tayo sa slide 7. Ay 27 pa. 27. Yung start itong these figures no. So in your paper you said na magkaiba these axial and transverse figures, they show different things. Yung sa transverse, it shows the amplitude of the wave. Is that correct? And yung axial is yung brightness, intensity. Is that correct?
Actually, as I was running the results po, a long time after I finished the draft, I realized na it's not actually the amplitude. kasi the amplitude is actually connected to the intensity of the image.
Okay.
So what happens in the but the axial is the intensity or the
Okay.
brightness.
Eggshell is the brightness. Okay. Then the
Apa.
transverse is
And then the transverse is the translation at the XY plane nung focus.
So, saan yung
okay.
Clarification, Steph. Are
I
they showing both intensity or
sorry. They're both intensities po. They're both intensities at
Okay.
different
Different planes.
yes. Sorry.
Okay. So how do these two results create a better image? So that's my question. What are we looking for? Well, we want a good well-defined image, no? For a good telescope. So what are we looking for? Yung red ba? Yung is that the red dot?
Yes, we're looking for the red dot, and if possible, uh, we're also looking for the smallest width of the red dot. So
Okay. So anong nangyayari is what happens when you have two dots? What does that look like? For example, you have a basic image of for example, a planet. Will I see two planets if we have two dots?
Well, yes.
Okay.
If the telescope was made to see the two for you to be able to see the two foci, you would see two planets if you were imaging the same object.
Steph?
Okay.
I think just to follow up to the question of Mr. Agapito, if you're looking at 160, compare it with what you're seeing at 38. I think mas iba yun 160. Yung nasa upper left at
Upper left and then lower right.
ang makikita mo say Saturn.
Okay, so okay po. So if you're imaging Saturn, so when you have this point spread function, you're going to see it with details, or like clearly you're going to see Saturn.
Okay.
When you have this point spread function at this distance, you're going to see two bright blobs, or I am assuming that appear to be Saturn, but you can't really be sure kasi it's not clear and the details are not seen well.
Okay. So it looks like the optimal distance between the two mirrors is at 60.
This is for side by side po.
Side by side. Okay.
Sorry.
So for parabolic, for example, the best distance is somewhere around here, 38, 48.
Yes.
Okay. And these are all tilted at the same angle.
They are tilted based on the distance.
On where they lie on the parabola.
Yes.
Oh, okay. So which of this is the the best image? Which one would we want? For example, we're building a segmented telescope.
Well, based on the final results here. Okay. So based here, since for the other results, the circular and parabolic configurations are sort of comparable, but when measuring the full width at half max, it is actually the values for the FWHM of the parabolic configurations are lower than for the circular configurations. So it is more ideal to have a parabolic configuration. If i-compare sa circular, sa side-by-side, and sa side-by-side.
Okay, okay. Another thing, can you put the slide dun sa where you derive the equation for the parabola and the circle?
Okay. Wait, sorry.
Because so I noticed na you use you the way you did this is you have a value for the focal length, right? Or the diameter. Is that correct?
For the focal length.
Okay, the focal length. So um I think I have a suggestion here. Maybe you can do a version of the derivation where you use a general quantity for the focal length. And then from that, I think you can I don't know if this will work. You can find an optimal distance that is based on your generalization. So you're only given a diameter of the mirror, and then you'll be able to solve like a range of values that correspond to an optimal distance based on that equation of the parabola or the circle. I think that could be an interesting addition, no, to your work. This is
Sige,
kind of interesting,
sige po,
Okay.
I'll try to do it po.
Pwede ba? Okay, sige. What else? Yeah. Okay, so
May iba
yun
bang configuration aside from circular and parabolic?
Po,
Other configuration than circular and parabolic? Or yan yung pinaka-ideal ba?
actually, sir, I just worked with the assumption na since it in calculus, the parabola and the circles align. Yes, sir po.
Rafi. Actually, yan lang pinagawa sa kanya. Pero, one general form of this is just try to imagine not a segmented telescope, but an array of optical telescopes around the Philippines, for example, randomly distributed. What would be their contributions to each other? That's one of the, or a random distribution of mirrors, non-overlapping, of course. So this one is actually just one step from doing that. What we wanted to see is what's the general form of the PSF given a distribution of mirrors, not necessarily on a parabola circle. So, syempre ito yung ginawa natin para madali. Pero marami pang ibang configurations na pwede. You can just imagine it's a 3D space.
parang practical to, no, yung ginawa mo kasi 2 mirrors lang and can easily test it if you're like a hobbyist, no? Pwede mong i-try agad. Okay. Another thing is, di ba you have a minimum distance here? I mean, kasi like the mirrors, they can't overlap, right? So my
Yes.
question is, will the size parang magko-compensate ba yung size nung tawag dito, will the size of the curved mirror compensate for the distance between them? Kasi lalaki ng so for example, you're using bigger mirrors, there's going to be a minimum distance between these mirrors, right? Because they can't overlap.
Yes.
So, like, will the size of the mirrors be a limiting factor to this configuration? Kasi paano kung sobrang laki na ng mirror mo? It's like 1 meter in diameter, right? 1 meter in diameter. If you have that configuration for just ano sa tingin mo lang, no? If you have that configuration, you have a 1 meter mirror, will that limit, parang, will that still produce a good image? You have a mirror that's 1 meter in diameter, 2 mirrors pala.
So like yung diameter ng segments ay 1 meter.
Yes. What if they're bigger?
I actually don't know if merong limit to that. I think part siya nung recommendation of like
Okay.
varying the diameters of the mirrors used. So I can't say exactly, pero I think as long as they are properly aligned, it would still work.
Okay, I see.
Nasagot naman niya, pero may answer na kasi yung tanong mo. In Alagao's work in MS, ang limitation niya would be, it's all really dependent on the diameter of the component segments. So, yun na nagde-determine talaga ng resolution. Yung component segment. So, kung gusto mong lakihan yung component segment mo, ang effect niya, gaganda yung resolution. All the segmentation will do is to just increase the intensity, not really make your resolution better. So, yun talaga yung kaya, hindi rin maganda palagi na mag-segment ka kasi lumiliit yung resolution mo. Pero nakikita mo mas maganda. Pero hindi mo nare-resolve yung resolving power yung nagsasuffer. But that's out of the scope of
okay, sir.
just to answer, mahirap nakahang yung tanong eh.
Okay. Okay. So, yun muna. Hanggang dun muna yung questions ko. Thank you.
Thank you po.
Okay, so my questions from audience. You can raise your hand and feel free to ask.
I have one more comment. I think this will be an interesting addition if you plan to expand your work. So, if you have more than two mirrors, you can arrange them along a single parabola, right? You can arrange them along a single parabola and you can study its effects. But it will, maybe you can also so from one mirror, you add another mirror. And then from that second mirror, you create another parabola. It's going to be different from the first parabola. And then you add the third mirror there. And what could be the result there? So I think that's an interesting addition.
Okay, I'll take note of that po.
Okay. All right, so that's all.
Hindi naman yung papagawa, di ba?
Yeah.
Yeah. Pwede
Okay.
actually siya na.
Recommendations po.
Ang importance kasi ngayon ay steerable. So, if you want to make your individual segments even steerable, that's the parabola on a parabola on a parabola that you're talking about. So, maybe not in imaging, but in solar concentrators.
Okay.
Doon siya magiging kasi may problema ka sa image. O marami ng segments baka hindi ka kagaya ng results ni Steph, can you show the one with parabola 33, 34? It's not really easy, either of those. It's not really easy to make them coincide if you're in a parabola because hindi naman talaga siya exactly mag-lock in into one point kasi tilted nga yung yung light rays mo. So hindi talaga siya mag-converge to a smaller point. In fact, you go to even a little bit worse than a single mirror. But you can increase the intensity. So, kung ang habol mo ay hindi imaging, ibig sabihin, wala kang pakialam sa resolution, kundi puro intensity, then that's where you can steer everything. Basta mag-a-add up lang. Ang maganda lang naman sa intensity, they add up. Eh. So, energy just adds up. So, if you just want to concentrate it into one point. So, actually, yun yung magandang result, I think, here, that you get. It doesn't have to be side by side. Can you show that one, Steph?
Ito po.
The other one, before one, 36. Yeah, it doesn't have to be side by side, which is 38. It can be a little bit further away, which is 48, 40. So, ibig sabihin, may luwag ka ngayon sa design mo, sa engineering. Pwede ka maglagay ng struts in between kasi hindi, paano mo naman support yung mirrors, di ba? So, I think we were trying to do this. Steph originally tried to do this physically. Had we known this way before, then pinipilit niya pagtabi-tabihin dati. Tinitipid niya lahat. So, pwede palang magkakahiwalay. So, well, that's what you get for COVID.
Yes. Okay.
Which is good. Anyway, so that's it. Thank you.
Okay. So maybe last question na lang from me. Ano yung best telescope in development niya? And sa atin, sa Philippines, ano yung status natin? Kung compare mo dun sa mga gumagawa ng mga telescope in other countries.
As far as I know po, wala atang I'm not sure if yung Celestron or Cutting Edge, which are stores that sell telescopes, if they are Filipino or if they are making their own telescopes. Pero as far as I know po, for now, wala po masyadong nagfo-focus sa telescopes since yung from what I know po from the Philippine Space Agencies and other references that I've read, more on satellites po yung focus ngayon ng Philippines. Tapos medyo hindi ko rin po alam yung context in other worlds, pero I think yung best telescope po ngayon ay yung James Webb Space Telescope.
Segmented.
Which is a segmented telescope.
Okay.
Also, marami din tong segmented telescopes na currently in the works in different parts of the world. The Giant Magellan Telescope, the extremely large telescope po. Those are real telescopes. Yun po talaga yung pangalan niya. Tapos, they are all segmented. So, ayun.
The best telescope in the Philippines is the one in Pag-asa.
Yes, ayun po pala. The largest telescope.
NIP.
Sa may tambayan po ng astro.
Okay yun.
Pero may gumagawa rin ng segmented telescope and she's the one presenting right now. Kung makabalik siya sa NIP.
Okay.
Wala talaga. Lockdown eh. Anyway, so yun yung that was the original extent, the original plan for her thesis is to build one, not just simulate one.
Mm.
We're here. But if she has time to get back, when we get back, nandun pa rin yung mga mirrors niya. So, naghihintay lang siya na magawa. So, iyon actually, parabola that will be, parabolic mirrors that will be configured in a parabola. So, we'll see kung ano abutin. And that will be the largest segmented telescope in the Philippines. 7 times 210 millimeters. So, not really good. And last comment for the audience as well. The telescope community in the Philippines is really yung amateur telescope community imports kasi. So, pipili ka lang sa Lazada, sa Shopee. Makakagawa ka ng mga 8 inches telescope, etc. Pero yung research on making new ones or combining, say, the 8 inches together, wala. Well, si Steph na yun. Saka si Angeli, which left nasa Thailand ngayon. So, she has her larger telescope. So, yun lang. For context. Thank you.
Okay.
Okay, so we're looking forward to Stephanie in making the best telescope in the Philippines. Okay, so if there's no more questions, we would like to thank Stephanie Vergara for her presentation.
Thank you.